Hello everyone. Welcome to 11th discussion session of the course Strength of Material course offered by NPTEL. Uh, the course instructor of this course is Professor Shriman Kumar Bhattacharya. He is a professor from IIT Kharagpur. Myself, Asif Raza. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. I am the TA of this course. So this is the 11th week of the discussion session, and uh, uh, this is I would say this is the second last session. After this, there would be one more session that would wind up the discussion sessions. So for today's session, it would involve the questions relevant to assignment number 11, which is prominently related to columns. So before discussing the questions, I'll just try to give a brief important things which are needed to solve the assignment. So let's start. So the topic of this week is columns. So columns are normally a vertical structure member, normally fixed at both ends, and an axially compressive load is applied. Okay, so uh, few things which I want to tell you is about the Euler buckling load. So it is given by the relation pi square E I minimum upon L E square, where PE is Euler buckling load, E is modulus of elasticity, I minimum is the minimum uh, moment of inertia about centroidal axis. LE is effective length. So I would just say something about this effective length. So this is one thing. So effective length. What is effective length? So if the member which you are considering, it's fixed at both ends, and the length, actual length of the system is L. So effective length LE for both ends fixed, it's L by 2. Okay, this is first one. Second one, when one side is fixed, other side is free end, kind of a cantilever, then, and its length is L. The effective length is 2L. Okay, so third is when let's say both ends are hinged. Hinged. Effective length is L. And the last one, take is when one end is fixed and other one is hinged, and the length is L. So effective length in this case is L by root 2. Okay, so this is the thing which I wanted to say. Now the other thing, it's called as slenderness ratio. Slenderness ratio, it is the ratio of the effective length and the least radius of variation. So if you it is denoted by lambda, thus I can write lambda is equal to LE by R minimum. Okay. Now if you see the relation for Euler buckling load, PE is equal to pi square EI minimum upon LE square. So there's one thing can be done about it is I minimum is equal to A times R minimum square. Okay. Now I can write PE as EI plus minimum by lambda square. Then again it can be written down as pi square E A R minimum square. Sorry, it was LE square here. So LE square again simplified as EA R minimum LE square. Thus it can be written down as pi square EA upon lambda square. So this is also one way to find the Euler buckling load. If we are given with the modulus of elasticity, area of the system considered, and the slenderness ratio, then we can directly find what would be Euler buckling load. The last one regarding this which is needed is Rankine load. Okay, and that is given by, suppose if PR is my Rankine load, so that is given by PC plus PE, where PE is the same thing, PC is sigma C times A or sigma Y times A. It's a crushing stress. Okay, so this is it which are needed for today's session. So what all things are needed? Euler buckling load and related to effective length, what's the slenderness ratio, and the expression of Euler buckling load in terms of slenderness ratio, and the Rankine load. Okay, so let's start discussing questions relevant to assignment number 11. So first question is Rankine-Gordon formula for buckling of columns is valid for options are long columns, option B short column, option C short and long columns, option D very long columns, and the correct answer pertaining to this question is option C short and long columns. Okay, moving on to the next question. Slenderness ratio of a column is defined as the ratio of its length to its options are least radius of gyration, least lateral dimension, maximum lateral dimension, maximum radius of gyration. Just now I told you about the slenderness ratio, that it is the ratio of the effective length and the least radius of gyration. Thus, correct answer would be option A, least radius of gyration. Okay, moving on to the next question. From here onwards, some calculations would be required. So let's start doing these questions. The first question is a 2-meter long column with square cross section is pinned at both ends. The side of column cross section measures 300 mm. The slenderness ratio of the column to the nearest round figure is. So let's write what all things are given. So it's a square cross section, right, with write this as B. So we are given with B as 300 mm, right. Length is 2 meter. I can write it as 2000 millimeter. Now, boundary condition is pinned at both ends, and we need to find the slenderness ratio of the column. To find the slenderness ratio of the column, it's given by lambda is equal to LE upon R minimum, right. Now, first thing, what would be my LE? And LE depends on my boundary condition. So let's see. The question is it's pinned at both ends. So if you see option C, my effective length is equal to the actual length. Thus, for this case, LE would be equal to L, that is 2000 mm. To find R minimum would be equal to I minimum upon area root. Okay, and this would be equal to, so since it's a square, so it would be I minimum would be B4 upon 12 and area would be B square. This can be written down further as B square by 12, and thus R minimum equal to B upon root 12, that is 300 by root 12. Find the value. So this is 300 by root 12. So this comes around 86.6 millimeter. Now to find slenderness ratio lambda, that would be equal to 2000 upon 86.6. This comes around 23.09. when rounding it off, I can write it as 23. Thus my answer would be option B, 23. Yeah, it's a quite easy question. Let's move on to the next question. Question number 4. If the failure stress in the material of a mild steel is 330 megapascal, Euler's formula for buckling load is applicable for slenderness ratio equal to or greater than. Given Young's modulus is 200 gigapascal and proportional uh, stress at proportional limit is 250 megapascal. So let us write. Uh, so failure stress is given to be 330 megapascal and stress at proportionality limit is given as 250 megapascal and Young's modulus is given as 200 gigapascal. I can write it as 200 to 10 power 3 megapascal. Now further, so Euler's formula for buckling load is applicable for slenderness ratio. So for this question, Euler's formula must be applicable, and uh, 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 applicability of Euler buckling load, Euler's formula is the critical stress must be less than equal to proportional stress at proportionality limit. Okay, thus uh, thus our P E upon A or sigma E, that is P upon A, that is E must be, this is, so sigma E must be less than equal to sigma PL, and this can be written down as pi square E lambda square must be less than equal to sigma PL. Let's substitute the values, or let us substitute the values first. So pi square E is given as 250 into 10 power 3. Sorry, 200 into 10 power 3. Lambda square less than equal to, at proportional limit it's 250. Yes, you can write it as lambda square must be greater than equal to pi square into 200 into 10 power 3 on 250. Let's solve this. So lambda square must be greater than equal to 7895.68. I just need to take the root of this. So it comes around 88.8. So as a round figure I can say lambda must be greater than 89. The correct answer pertaining to this question would be option B, 89. Uh, so moving on to the next question. Question number 5 is the ratio of Euler critical buckling load of two columns having same parameters with one end fixed, one end free, and the second is both ends hinged is. So if you remember, it's given that parameters are same, and the formula for Euler buckling load is pi square E I minimum upon L E square, right? So if all the parameters are same and the boundary conditions are only changing, then our LE will only change. So if I take the case PE for the first condition where one end fixed, let's say one end fixed, one end free. So if you see what I told earlier, one end fixed and one end free, one end fixed and one end free. Option B. So effective length is L equal to 2L, right? So we need to use that thing. So for this case, LE is equal to 2L. Thus we can write Euler buckling load for this case as pi square E I minimum upon 2L square, that is 1 upon 4 times of pi square E I minimum upon L square. Now for the second condition where both ends hinged, both ends hinged. The effective length for this case is, let's see, both ends hinged. Option this C, the third one. So this is L equal to L, right? So effective length for this case is L equal to L. Let's use that. Now correspondingly my Euler buckling load would be pi square E I minimum upon L square. Thus it's just pi square E I minimum upon L square. Now the question is asking the ratio of these two. The question is asking what would be PE1 upon PE2, and if you see it comes around 1 by 4, that is 0.25. Thus my correct answer would be option D, 0.25. I hope there's no issue in this question. It's a straightforward, just the use of this formula and the application of the substitution of the effective length respective to the different boundary conditions. Okay. If you have any doubt, you can just ask anytime. Moving on to the next question now. So question number 6. A 3-meter long circular steel column with outer diameter as 40 mm and inner diameter as 30 mm is hinged at both ends. Yield stress of the column is 300 megapascal and Young's modulus is 200 gigapascal. Critical value of stress, that is stress at proportionality limit, is 200 megapascal. Compute critical load using Rankine formula. So if you remember, the Rankine formula was given by this relation. So So we are given that this is the Rankine formula. We can find the Euler buckling load, we can find this crushing load, and just use the substitution of this, and we can find the Rankine load. Okay, so let's solve this. So let's before that, let's write what all things are needed. Okay, so first thing is length is given as 3 meter, that is 3000 mm. Outer diameter as 40 mm, inner diameter as 30 mm, hinge at both ends, implies the effective length would be equal to L, and that would be 3000 mm. Yield stress is 300 megapascal, Young's modulus is 200 gigapascal, that is 200 into 10 to the 3 megapascal. Stress at proportionality limit is 200 megapascal. So first thing first, to find the Euler buckling load, we need to find moment of inertia, and that can be found by pi d naught 4 minus di 4 164. Let's substitute this and find it. 44 30 to the power 4. This will come out to be 40 to the power 4 30 into 5. So this comes around 85902.92. Okay, let me cross check it once again. 40 mm, right? Yeah, so 40 to the power 4 minus 30 to the power 4 into pi divided by 64. Yeah, so this is okay. Area is pi d square by 4. So 40 plus 30 square, this is 40 square minus 30 square into pi by 4. This will be 549.7778 millimeter square. This R can be by taking this I upon A, and this would be 85902.92 549.78. This comes around, so 85902.92 divided by 549. This comes around 12.49. I'll just write it as 12.5. Now this is done. There's my PE is equal to pi square E I upon LE square, that is pi square into E is 200 into 10 power 3, I is 85902.92, LE is 3000 square. So let's find this. 200 into 10 power 3 into 85902.92 to pi square divided by 3000 square. So this is 8. This comes around 18.84 kilonewton. Okay. Now PC would be sigma y upon A, and sigma y is 300 times A is 549.78. This would give me Newton. I need to find it kilonewton. So 300 into 549.78, this would be 16.49 kilonewton. I can use this formula now, 1 upon PC upon PE, to find PR, and 1 upon PR is 1 upon 16.49 plus 1 upon 18.84. Uh, 84 plus 1 given by 16.49. This comes 1.1137. Thus PR is 8.79 kilonewton. Seems like there is some issue. Let me do it with a different way. Now okay, let me try to do this in a different way. Rankine load equal to sigma ya plus 1 upon sigma y upon pi square E LE upon R square. And this can be written down as 500 into 549.78 divided by 1 plus not 500, 300 pi square E is 200 into 10 power 3, LE is 3000, R is 12.5. Let's see. Okay, I made a mistake here. It was 164.93 kilonewton. That's why answer was coming abruptly. Nonetheless, let's calculate it the way I'm doing right now. So 3000 divided by 12.5 whole square into 300 divided by 200 divided by 3 divided by 5 plus 1 to the power minus 1 into 300 into 549.78. This comes around 16909 Newton. Thus I can write 16.9 kilonewton. Okay. Okay. We do the cross check once again. 549.78, 16.93 pi square into 200 into 10 to the power 3 into 85902.2. Yeah, so this is correct. 1 by 1804 plus yeah, so here it was a mistake. Now if you try to use this formula also, 1 upon PR equal to 1 upon PC plus 1 upon PE, this will also result in the value of 16.9 kilonewton. Okay, this answer would be option B, 16.9 kilonewton. Okay, moving on to the next question. Question number 7. An I section steel column has 3 meter effective length. Find the safe load carrying capacity of the column using the Rankine's formula, allowing a factor of safety of 3. Consider E is equal to 100 gigapascal, sigma Y is equal to 320 megapascal, Ix second moment of inertia about x-axis is this and y-axis is this, area is this. Okay, now to find the radius of gyration we need to take I minimum. Okay, and if you see, I minimum is I by y, that is 2.1936 into 10 power 7 4. Okay, area is 7485 meters square. The parameters are sigma y is 320 megapascal, E is 200 gigapascal, effective length is given as 3 meter, so I can write it as 3000 mm. I write E as 200 into 10 power 3 megapascal. Also a factor of safety, that I write it as F, and that is given as 3. Now let's solve it. So first thing first, what would be my radius of gyration? That would be I minimum upon A, that is 2.1936 into 10 power 7 upon 7485. Let's do this calculation. So 2.1936 into 10 to the power 7 divided by 7485 to the power So this comes around 54.135 mm. Now to find the Rankine load, you can use this formula. Okay, so let's substitute whatever is provided. 320 into area is 7485, 1 plus sigma y is 320, pi square e is 200 into 10 power 3, effective length is 3000, radius of gyration which we found is this. Can write PR. So PR equals to, do the calculation, 320, 3000 divided by 54.135 square into 320 divided by 5 square divided by 200 into 10 to the power 3 plus 1 to the power minus 1. So into 320 into 7485. So this comes around 1599082.298 Newton, or you can write PR is 1599 roughly kilonewton. So safe, this is a Rankine load. We need to find safe Rankine load. Is PR upon factor of safety, that is divided by 3, right? So this comes around 533.03 kilonewton. The answer is option D. Moving on to the next question. Question is, a cantilever column of wood 3 meter long with a rectangular cross section carries a load of 80 kilonewton. Determine whether or not a section of size 200 mm by 150 mm will be able to carry this load if a factor of safety 2.5 is to be used as per Euler's buckling load, given Young's modulus as 12.5 gigapascal. So in this question we are given with various parameters, and we need to find that will this system would be able to carry 80 kilonewton load or not. So let us write first what all things have been given. So it's a cantilever system, it's a cantilever column, length is 3 meter 3000 mm. Since it's a cantilever column, effective length would be twice L, that would be 6000 mm. Okay. The rectangular cross section carries a load of P is given as 80 kilonewton. So it's a rectangular cross section. Okay. B and D. So B is given as 200 mm, D is given as 150 mm. factor of safety is 2.5 and X modulus is 12.5 into 10 power 3 megapascal. So let's find. Let us find what would be my Euler buckling load for this system. The Euler buckling load is given by relation pi square E I minimum upon L E square. So to find this, we need to find I minimum, and that would be BDQ by 12, and that is 200 into 150 cube by 12. That comes around 56.25 into 10 to the power 6 millimeter. PE would come around pi square. Let's substitute it. 12.5 into 10 power 3 into 56.25 into 10 power 6 divided by 6000 square. Six point two 6.25 into 10 to the power 6 into 12.5 into 10 to the power 3 into pi square divided by 6000 square. This comes around 192,765.71 Newton. PE can be written as 192.765 kilonewton, but this is still not the according to the safety factor. So safe Euler buckling load would be PE by factor of safety, and that is 192.765 divided by 2.5, and this is equal to 77.106 kilonewton, and this is less than 80 kilonewton, which is what is being applied in the system. So as my system is only able to carry this much amount of the load, and the load is provided as 80 kilonewton, it won't be able to sustain. Thus our correct answer would be that it's an inadequate to carry the load, that my system won't be able to carry this much load, is inadequate to carry the load. So so please look carefully how we have found this thing. So with the given parameters, we were able to find the Euler buckling load, and then we divide it by the factor of safety, and it comes around 77 kilonewton, which is less than the applied load, that is 80 kilonewton. Since my safety limit is till 77 kilonewton, so it won't take the load 80 kilonewton. So thus we would say it's an inadequate to carry the load. Okay. If you have any doubt, you can ask. Similar to this question, I have also put up in the last part of this question. So in this question, this is a pin end column. Rest other things are same, and the factor of safety is also changed, like 2.5 to 3. So it's a similar thing. You just need to check the effective length and the factor of safety and check whether it would be able to carry the load or not. Okay. So I hope you would be able to solve this question as well. Now let's solve this question. Question number 10. Okay. So question is a pin and steel column. Young's modulus is given as 200 gigapascal. 2 meter long, is constructed from circular tube with outside diameter as 50 mm as shown in the figure. The column supports an axial load of 25 kN with a factor of safety 3 with respect to the critical load. Okay. The required thickness T of the tube is. Okay. Okay. We need to find the thickness for this system. We are given. Okay, let's write it down first. What all things have been provided. So it's a pin-ended steel column. Steel column. That implies that my effective length would be equal to the actual length. Okay. Given Young's modulus is 200 gigapascal. So I'll write it as 210 power 3 megapascal. Length is 2 meter, so 2000 mm. Outside diameter is 50 mm. Okay, so if my outside diameter is 50 mm and thickness is T, my inner diameter would be what? So my outside diameter is 50 mm and this would be my di. So di would be equal to what? D naught minus 2t, that is 50 minus 2t mm. Okay. What else? Yeah. So given is axial load is 25 kilonewton and the factor of safety is given to be 3. With respect to the critical load. So as we know, the safe load is found by taking the division of the critical load with respect to factor of safety. So my critical load PE with this would be what? PE times factor of safety. Okay, that is 25 into 3, 75 kilonewton. Okay, now let us find this critical load using Euler buckling load. Can write this as 1. So Euler buckling load. With that, I can write it as I minimum upon LE square. Okay, that is P equal to pi square. E is 200 into 10 power 3 upon LE is 2000 square. Now I minimum is pi 4 T naught minus Ti. Okay, let me write it here also so that it becomes easy for you all. Okay, D naught minus Ti. Okay, so this is 50 This is 50 minus 2t. So, 2. So from I can write is 75 into 10 power 3 Newton. So from 1 and 2 can write as 75 into 10 power 3 into pi square into 200 into 10 power 3, 2000 square pi by 64, 50 to the power 4, t minus 2t to the power 4. Let's do the calculation. So I can write it as 70 into 2000 square divided by 200 into 64 divided by pi cube. So 50 to the power 4 minus 50 minus 2t to the power 4. This comes around 3096,147.3055. Again, this can be simplified as 50 minus 2t to the power 4 equal to 3153,852.6944. Again, it can be written down as 42.14. Thus 2t would be 50 minus 42.14, and the thickness will come out to be 7.86 divided by 2. This comes around 3.93 mn. So let's check all the options. 3.93 mm. Yeah, so answer is option A, 3.93 mm. So it's just the substitution of the formulae. Only you need to do the calculations properly, otherwise you might make mistake. So it's just it's a pin-ended system, so effective length would be equal to the actual length. Young's modulus is given, the actual length of the system is given, outer diameter is given. We need to find the thickness. So inner diameter is what? D naught minus 2t. The given load is 25 kilonewton with a factor of safety 3 with respect to the critical load. Since there is a factor of safety 3, so the critical load would be what? 25 times 3, 75 kilonewton. Now the critical load, this critical load can be found using the Euler buckling load expression, that is pi square EI minimum upon LE square, and I minimum can be found by pi d naught pi by 64 times d naught to the power 4 minus di to the power 4, and this is one and the same, and using the simplification we can find the thickness of the system. That comes around 3.93 mm. I hope this is just the substitution and then the calculation, so you better check it properly. If you have any doubt, you can like ask anytime. Okay. Okay, moving on to the next question now. Okay, this is also a very interesting question. It's a simple question, you just need to see it properly how to solve this. Okay, so question is, two pin-ended columns of the same material, same length, are free to buckle in any direction. Uh, Both the columns have same cross-sectional area but different cross-sectional shape as shown in the figure. The ratio of the critical loads P1 upon P2 for these columns is, so we're given like two pin ended system, so LE would be same for the both LE1 and LE2. I just write this as this thing. Then E is same for both E1 and E2. Same length, so L is L1 equal to L2. Free to buckle in any direction. Both the columns have same cross sectional area, so A1 equal to A2. Okay. Only thing different is the shape. Everything is same. So let's find what would be the ratio of the critical loads P1 times P2. To find the critical load, the expression to find the critical load is pi square E I minimum upon LE square. Okay. So if you see in this case, pi would be same for all, E would be same for all, LE would be same for all. Only thing different would be I minimum. Okay. Now this can be further simplified. Okay. So let's do this. Do this case by case. So first one, the square one. I, if I take, okay, so I minimum can be written as b to the power 412 if my uh, what you say, the side of the cross section is given as b, so I minimum can be written as b to the power 4 upon 12. Since area is same for both the cross section, we want to convert this I minimum in terms of cross sectional area only. So I can further simplify I minimum as a square upon 12, because if you see a is equal to what, b square. Okay, so okay, so I can write this as I minimum 1. Thus my PE1, or rather its question says P1. Okay, so P1 is P pi square I a square upon 12 LE square. Okay, first thing. Second one, circular one, circle. For this I minimum 2. If the cross section is D, so the diameter of the cross section is D, what would be my second moment of inertia? Prag, if you are there, can you like engage yourself and let me know what would be my second moment of inertia for a circular cross section if the diameter is D? Are you there, Prayag? Prayag, are you there? Okay, no nonetheless, I'll just solve this. So, for circular cross section, second moment of inertia is given as pi d4 by 64. And if you know area for a circular cross section with d as a diameter, it's given as pi d square by 4. So I can write I minimum in terms of area of the cross section as pi d square by 4 whole square upon uh, 4 pi. Okay, that is I mean to a square upon 4 pi. Thus my P2 will be written as pi square e a square upon 4 pi le square. So let me write this. I can simplify it further. 1 upon 12 pi square e a square le square. P2 as 1 upon 4 pi square e a square on le square 2. This now I can take the ratio of both these, P1 upon P2. It will be 1 upon 12 divided by 1 upon 4 pi. This will come out to be pi by 3. Yeah. So let's see. Yeah, so the first option itself is the answer, pi by 3. Okay, I hope it's clear. It's quite a straightforward thing. Everything is same for the given problem. Like boundary condition is same, the length of the system is same material is used, same cross sectional area is there. Only difference is the shape is different. So as we and we need to find is the ratio of this critical load. So first thing is we know the expression of the critical load as pi square times E times I minimum upon LE square. So pi square E and LE would be same for all. I minimum would change. So I minimum can be written down in terms of area, which is also same for both these systems. So if we write that and then like take the ratio, then it becomes an easy calculation. So the bracket thing, this is same for all. So only thing would be 1 upon 12 for the first case and 1 upon 4/5 for the circular case. Then when we take the ratio of these two, it will come out to be pi upon 3. Okay, so this is it. Moving on to the next question now. Question number 12. I think I have left a question midway. Yeah. Okay, I'll solve this later. Let's solve further questions first. So this question is for a 5-meter long steel column with both ends fixed. Find the load carrying capacity of the column using Rankine formula. Given with the Young's modulus, proportional limit, sigma y, rx, y, different parameters are given. Let's find this. We have already done. Let's do it quickly for this case. So its length is 5000 mm, both ends fixed. Thus my effective length would be 0.5 L, and that would be 2500 mm. E is 200 into 10 power 3 megapascal. Sigma PL as 200 megapascal. Sigma Y is 250 megapascal. Rx is 180 mm. Ry is 30 mm. Yy is 834 into 10 power 4 millimeter 4, and area is given as 9272 millimeter square. So if you see both these two, so with this we can find that R minimum, or the radius of least radius of gyration, would be the Ry, and that is 30 mm. Okay. Let's do further calculations. So we need to find the Rankine load carrying capacity using Rankine formula, and that is PR is given by sigma YA 1 plus sigma Y pi square E LE upon R minimum whole square. Okay, let's do the calculations. So sigma Y is 250 into area of this cross section is 9272. 1 plus sigma Y is 250, pi square E is 200 in 10 power 3. This is 2500. R minimum is 30 square. Let's do the calculations. So 2500 divided by 30 square into 250 divided by 200 divided by 10 power 3 divided by a square into 250 into 9272. So this comes around 1233.290. 1233.290.8748 Newton. So I can write now as 1233.29 kilonewton. Roughly, by rounding it off, I can write it's 1233 kilonewton. Okay, so it will match with the option A, 1233 kilonewton. So it's also quite easy what we have been using, just the use of this formula. Okay, moving on to the next question, and this question is a straightforward calculation. Question is, if the Euler load for a steel column is 1000 kilonewton and failure load is 1500 kilonewton, the Rankine load is equal to what? So if you remember what I have told in the starting of this session, for regarding the Rankine load is calculated by this 1 upon PR is equal to 1 upon PC plus 1 upon PE, where PC is my failure load and E is Euler load, and PR is my Rankine load. So we need to use this particular formula to find for the given question. Okay, yeah. So the question, according to the question, we are given with Euler load as 1000 kilonewton and failure load as 1500 kilonewton. We need to find what would be my Rankine load. Okay, I will use this formula: 1 upon Pi equal to 1 upon P plus 1 upon Pp, 1 upon Pi, 1 upon 1000 plus 1 upon 1500. So this comes around this. My Pi would be 15 into 1000 divided by that is 1500 into 1000 divided by 2500. So this is this. So this will be equal to 600 kilonewton. This my answer is option D. 600 kilonewton would be the answer. Okay. Moving on to the next question. Okay. So before that, we'll solve this question, which I left it earlier. Yeah, this question. Question number 9. So this is a question which is, I think, it's similar to what is given in the assignment number 11. So it would help you. So please look carefully. Question is, a horizontal beam AB is pin supported at end A and carries a load P at end B, as shown in the figure. The beam is supported at C by a pin-ended column of square cross-section having 1.8 meter length and 60 mm side dimension. Based upon the Euler critical load of the column, determine the allowable load P if the factor of safety with respect to buckling is 2.5. Okay. So first thing, let me draw this. Okay, so if you see in the question, the load P is applied here. Okay, so we need to find the allowable load P in this case. So first, let us identify what is happening in this system. So when the load P is applied here, there would be this system would try to go down. So what would happen is this column would try to resist by applying R over here as this load P is applied. So this R would be this resistance R would be provided to this system from this load. So according to the Newton's third law, this same R would be applicable for this column, and that load would be kind of a compressive load, and that is what if that load is too high, then this column will start to buckle. So we need to find that limiting R with respect to which my this column will buckle. So if you are able to find that R, consequently we would be able to find the value of P for which my certain value of R will come, for which my this particular column will buckle. So I'll try to explain this by drawing that this system by two component way, taking the two different component. So if I take A B and C and R from this system, okay, so 2 meter would be this, 2 meter would be this. This is for this, and for the column it would be kind of this, but yeah, keeping in mind that it's hinged at both ends, okay, and length is 1.8 meter. Okay, so for this first part of the system, taking moment about A equal to 0, R will come out to be R into 2. This would be equal to P times 4. So R would be equal to 2P. Okay. This is first thing. Okay. Now let us find PE using minor buckling load. The PE is pi square E I upon LE square. Okay, we are given with a square cross section, right? The square cross section with side what 60 mm. So we are given with square cross section B equal to 60 mm, right? Yeah. This my I would be B 4.12, that is 60 to the power 412. This will come around to be 1080,000 millimeter to the power 4. Now this is pinned at both ends. So LE would be equal to L, and thus LE would be equal to what? 1.8 meter, that is 1800 mm. Let us substitute and find PE. Pi square E. So pi square E is what? 100 GPa. So 100 into 10 power 3. I minimum is 108 into 10 power 4. 1800 whole square. Let's do this. Pi square 200 10 power 3 0 8 0 divide by 1800 square. So this comes around 328,986.81 Newton. Or I can write it as 328.987 kilonewton. Now this uh, P this PE equal to R. Okay. Now we can write from 1, 2 and 3 that PE would be equal to 2P, that is P would be P by 2 and P by 2, that is 328.987 by 2 kilonewton. 328.987. This comes around 164.49. Roughly P can be written as 164.5 kilonewton. The answer would be option C. Okay. Let me cross check it once again if I am doing it correctly or not. Okay, I missed one thing. So there is a factor safety is also provided, right? So okay, so with that I can write safe P would be what? 164.49 upon factor of safety, and that is 164.49 upon 2.5. That is what is the factor of safety in this case, right? Yes. So divided by 2.5, it comes around 65.79 kilonewton. So this is what it will be correct answer. Okay, so correct answer is option A, 65.79 kilonewton. Okay. So look carefully this question. This question is quite important for the current assignment. The horizontal beam AB is pin supported at end and carries a load P at end B. So as this load P is applied, there would be a resistive load at point C from the column CD, and this resistive load is would be acting as a compressive load for the column CD, which will at a certain point make the column CD buckle. So we need to find the load P for which the column CD would start to buckle. So for that we need to find first what would be the Euler buckling load for the column CD. Consequently, we would be able to find the relation between P and this Euler buckling load PE. and with the given factor of safety we can find what would be my actual safe load be. Okay, so that comes out to be 65.79 kilonewton. Okay, moving on to the next question, and this would be the last question for today's session. Yeah, so let's with this question, a hollow cast iron column with fixed end supports an axial load of 1000 kilonewton. If the column is 5 meter long and has an external diameter of 250 mm, find the thickness of metal required. Okay. Use the Rankine formula considering a constant of 1 upon 6400 and a working stress of 80 megapascal. Uh, this question, it's like uh, fixed ends, thus LE would be equal to 0.5 L. Okay, axial load is 1000 kilonewton. I can write 10 to the power 6 Newton. If the column is length is 5000 mm, external diameter T naught as 250 mm. We need to find the thickness. This di would be T naught minus 2T. That is 250 minus 2T mm. Find the considering constant. So alpha is kind of 1 upon 6400 and working stress is sigma is 80 megapascal. We need to use the Rankine formula. Okay. So to find the Rankine formula, we need to use this. So Rankine formula is given by this. For the given question, it would be sigma times A 1 plus alpha times lambda square. Okay, and sigma times A 1 plus alpha, lambda is what? LE upon R whole square. Right, so this is what we need to use. So let's calculate everything what all is required. So to find first let us find A. A is A is pi by pi by 4 t naught to the power 4 minus t naught square di square, and this will come out to be pi by 4 d naught square is 250 square minus di is 250 minus 2t square. Okay, this is my area. Now to find r, that would be I upon a root, and I is pi by 64 t naught power 4 minus ti to the power 4 upon pi by 4 t naught square minus ti square. This can be simplified as t naught square plus di square. T naught square minus di square, t naught square minus di square times 16. Thus r can be written, or r square can be written as t naught square plus di square by 16. Okay. Yeah. Okay. The further, so 250 square, 250 minus 2t by 16. So 250. Let us leave it here. Yeah. Let us substitute in the substitute 3 in 1. PR is equal to sigma is 80 by 4 250 square minus 250 minus 2t square divided by 1 plus alpha is 1 upon 6400 times LE square by R square, right? Yeah, LE is 0.5 L, so this would be 250 500 square. R square is 250 square plus 250 minus 50 16. Let's do the simplification. Now PR would be equal to this 1000 kilonewton, so I can write 10 power 6 here. Let's do the simplification. 10 power 6 times 1 plus 15400 into 2500 square into 16 25 equal to 80 times 5 by 4. This can be simplified with plus b, that is 500 minus 2t, 2a minus b, that is 2t. Okay, further simplification, so 10 power 6, 10 power 6 this up. So this is 1 plus this comes around 15625 divided by 250 square plus 250 minus 2t square. 20 b is 40 by t to 500 minus 2t minus 6. Okay, it seems like calculation is taking a bit cumbersome. So what I'll do now is I'll just use the substitution of the formulae from the option, and let's check which one of this will satisfy. So first is t equal to 39.5, 29.5, 19.5, right? So 39.5 equal to 29.5, 19.5 and 9.5. So let's do the substitution and check. So 40 LHS for this case is 250 square plus 250 minus 2 into 39.5 square. This comes around 2.08972. So I think this won't be the answer. Let's check for second option. 15625 250 square plus 250 minus 2 into 29.5 square into 15625 plus 1. This comes around 1.157858 RHS. Let's see, 40 into pi into thickness is 29.5 into 500 minus 2 into 29.5. 1.634821. Let's check the other one. This also same. Let's see the other one. So RHS for this case 40 into pi into 19.5 into 500 minus 2 into 5. This comes around 1.129653. 40 into 5, 29. LHS is 250 minus 2 into 19.5 square plus 250 square to the power minus 1 into 15625 plus 1. So this comes around 1.146. So this is a bit closer. Let's check the other one. 40. Check the other one. 250 minus 2 into thickness is 9.5 square plus 250 square to the power minus 1 to 15625 plus 1. This is 1.1348 RHS. 40 into pi into 9.5 into 500 minus 2 into 9.5. This comes around 0.574. So more probable answer should be option C. So both of these, like the probable answer of this is both these two, and if we see here it's more, so 157 146. So out of these two options, the one of them is correct, and to which I recall is answer comes out to be option B, 29.5. But it's best you guys look it up how to do this. Okay, and to this question I've already told you about that it's similar to what we have solved earlier. It's just the boundary condition is changed and the factor of safety is changed. So I hope this can be solved easily. To this I would like to wrap up the session here. If you have any doubt, like, you can ask. Prag, if it's okay, we can wrap up the discussion session here. I'll just wait for one more minute and see if you are there or not. Then we'll wrap it up. Okay, then it's already 1 minute. So I'll end the session here. I hope you don't have any doubt. If you have any doubt, like, you can post it in the discussion forum as well. I'll be more than happy to resolve your doubts there. Okay, ending the session now. We'll meet in the next Saturday, same time, 4 to 6. And that's it. Have a nice day. Take care, everyone.